All right, and now we will do Chapter 8, Applications. So we'll be putting to use some of the concepts that we talked about in the last video. So for our first example, we're looking at a gas that is expanding from this volume to this final volume. And we see that the pressure is increasing linearly from 110 to 230 kPa. So we want to find the work done by the gas. The first thing we should do is sketch that. And again, y'all know that my sketching abilities aren't the best on here. So this is what it would look like. So I've plotted my pressure versus volume, and you should have pressure on the y-axis and volume on the x-axis. And once you graph your points, this is what we have. And you'll see that even though the entire shape would be difficult to find the area of or find the work for, it's easier if we split it into a rectangle and a triangle because we're more familiar with the area formulas for those shapes. So let's begin by using the fact that work is equal to the area under the curve. So let's find the area of the rectangle and then the area of the triangle, add them together, and that'll be our work. So for the area of the rectangle, we know that the area of the rectangle equals, we'll just say length times height. So the length times the height. And we know that our length is the change in volume and our height is the change in pressure. So this would be our change in volume and this would just be the change in pressure. So that means the area for the rectangle would be the final volume minus the initial volume. So that's 0.62 meters cubed minus 0.40 meters cubed. And then our pressure is going to be the final minus the initial. The final pressure, well, for this section, because remember, we're just looking at this rectangle. The final pressure for this portion is 110 and the initial was 0. So 110 minus 0 is just 110. So that's 110 kPa. That means the area of our rectangle is going to be equal to 2.4 times 10 to the fourth joules. Okay, let's do the same thing for the triangle. So the area of our triangle, I'm just going to draw that, it looks better. Area of triangle, recall from geometry, is 1/2 base times height. So we know our base in this case is going to be the volume and the height is going to be the change in pressure. So let's go ahead and plug that information in. So we have 1/2. The change in the volume, well, that's what we did last time. 0.62 minus 0.4. And the change in pressure, this time it'll be 230 because that's we see pressure here 230 and the beginning was 110 for this section. That is 110. Okay. So then the area for our triangle will come out to 1.3 times 10 to the fourth joules. So now to find the work, that's just going to be this total area underneath the curve. So let's add together the area from the rectangle and the area from the triangle. So that total area is going to be work. Again, we're just going to add these two values together and you'll find 3.7 times 10 to the fourth joules. So that would be our final answer for the amount of work. Okay. In this example, we have a gas that is being compressed adiabatically. So that's important, the word adiabatic. We know how much work was done to it, and we want to find the change in internal energy. So we are looking for delta U. Here's our question. We've been given work, and we know that this is an adiabatic process. Well, in order to do this, let's remember a few things. So first of all, what does adiabatic mean? If something is adiabatic, that means that Q equals 0. And we know we're looking for our delta U. So do we have an equation that relates delta U, the work, and Q? Yes, we do. It's the first law of thermo, which is delta U equals Q minus W. Well, we know that the work done on the gas is 730 joules. Now, since it says it was done on the gas, we know that work is negative 730 joules. So you got to pay attention to the wording here. Let's plug in what we know. Q is 0 minus negative 730 joules, which just means the change in internal energy is 730 joules. So it'll be a positive 730 joules. And that's it. Okay. Now we're looking at some container that has an initial volume of this, and it holds this many moles of some monatomic gas. Here is the temperature that it's holding it at. After the gas is compressed adiabatically, so no heat is flowing into or out of the system, we see that our new volume is this, and we want to find the final pressure and the final temperature of the gas. So one of these is going to be much easier to find than the other. We have been given several pieces of information, which is going to be very useful. So we were given our, we can't see that. We were given an initial volume. We were told the number of moles, which is N, and we were told the initial temperature. And then we were also given, that's not initial, the final volume of the gas. Since we need to find the final pressure, well, we can't do that unless we know the initial pressure. So let's go ahead and solve for the initial pressure because we already have the initial volume, the initial temperature, and the number of moles. And to find our initial pressure, we can just use PV equals nRT. And we're going to use all of our initial values since we're looking for the initial pressure. So let's rearrange, and we get P equals nRT over V. And remember, this is going to be the initial values for all of these. Just plug in what we have. So 2.45 moles. The R value, if you'll recall from the previous unit, is 8.0. That's 8.31. Oh, that's close enough. Joules per mole Kelvin. And our temperature is 325 Kelvin initially. Our initial volume is 0.0607 meters cubed. So the initial pressure is going to come out to 109 kPa. All right. Since we now have that, we can use the fact that it tells us this is an adiabatic process in order to solve for the final pressure. In the concept video, we discussed that an adiabatic process is going to have an extra little symbol. It's going to have this gamma. So we can use one of the ideal, not the ideal gas, but the pressure volume relationship in order to solve for final pressure, since now we have 3 of the 4 variables. So P1 V1 equals P2 V2, and we know that this is for an adiabatic process, so we need this little symbol. Okay, so let's go ahead and rearrange so that we're solving for P final, which would just be this term right here. So P2, which is going to be P final, will come out to P1, and that would be multiplied by this. Again, we have our little gamma up here. So let's plug in what we know. The final pressure is going to be equal to 109 kPa multiplied by, that's 0.0607, and that's meters cubed, over the final, which is 0.03 0.77 meters cubed. And then this gamma has a value of 5/3. So that's how we know what to put here. So when we solve for the final pressure, we're going to find that the final pressure is equal to 241 kPa. So there's our final pressure. But we're not done yet. We also need to find the final temperature of the gas. Now, since we have the final pressure now, we have that here, and we know the final volume, we also still know the number of moles. That hasn't changed. Solving for the final temperature is going to be very straightforward. We're just going to go ahead and utilize that ideal gas law formula. So PV equals nRT. We're solving for temperature this time. So the final temperature is going to be equal to the final pressure times the final volume divided by nR. Plug in what we know. And we're going to get 241 kPa. The final volume is 0.0377 meters cubed. N is 2.45 moles. And that R value is 8.31 joules per mole Kelvin. So when we solve this, we'll find that our final temperature is equal to 446 Kelvin. So that's how we would find the final pressure and the final temperature. Okay. And now we've come to a heat engine problem. So we have a heat engine and we're told the efficiency of the engine and we see how much work it performs. So we want to find the heat that is absorbed from the hot reservoir and the heat that's given off by the cold reservoir. All right, so to do this, let's think about what we have. We were given the efficiency and we were given the work. I don't know why this isn't writing here. This is our work. Okay, and that's our efficiency. So if you'll take a look at your formula chart, we actually have a formula that relates both of these and will allow us to find our QH. So the heat from the hot reservoir. That formula is that the efficiency is equal to QH over work. Well, we need to solve for QH. So QH is equal to the work divided by, multiplied by the efficiency. Let me erase that. Okay, so this is equal to the efficiency times the work, which is, okay, this is a percent, so we need to convert that, 0.24. And then work, which is 1250. And when we do this, we should find the following, which would be 5,210 joules. So that's going to be our QH. That's how much heat is from the hot reservoir. Now, to find the heat from the cold reservoir, so this is part A, and here is part B, then we have the following relationship. Work equals QH minus QC. Well, we have the work and we have our QH now. So to solve for QC, we're just going to do some very simple math. And we will find the following. So QC is going to be equal to QH minus W. So that would be 5,210 joules minus 1250 joules of work. So QC is going to be 3960 joules. So there would be our answer to this part. Okay, and just let me quickly clarify something because I just realized I wrote this backwards. This is, and I'll do it in a different color, work divided by QH, which means that QH will actually be the work over the efficiency. So then this does not go here, but down here. I knew something looked wrong while I was doing this. And yes, I wrote that backwards. So I apologize for that. All right, in this next one, we just have a conceptual problem. So something for you to think about. So take a moment, pause this video and read the scenario and then hit play when you're ready. Okay, so we haven't had time to install this air conditioner in a window. It's a window unit. So we just decide that since it's hot, we're going to put it on the dining room table and turn it on because we want to get things cooler inside the apartment or the house. So what's going to happen to the air in the dining room? Will it get warmer, cooler, or stay the same temperature, and why? So for this, the room is going to get warmer because the combined heat that is given off by the AC and then the work done by the motor will combine to actually make the room warmer. But if you were thinking that number 3 was correct, that there would be no difference, here is why number 3 was not correct and number 1 is correct. So the air conditioning is going to take in the heat from the air, and then it's going to give that heat off again to the room because normally that heat would be given off outside. So it's taking in heat and giving it right back off. That would keep the temperature the same. But in addition, there is a motor running in order to keep the air conditioning going, and that motor is also generating heat. So not only do we have the heat that's taken in from the air and given back off in the room, but we also have the heat being generated by the motor. So that's why it would actually get warmer if you had the AC just sitting on the table where the heat was not being exhausted to the outside. Okay. Now, in this one, we have a heat pump, an ideal heat pump, and it satisfies Carnot's relationship, which is written here. We're using it to heat a room that's at 293 Kelvin. And if that pump is doing this much work, then how much heat will be supplied to the room if our outdoor temperature is 273 Kelvin or if it's 263 Kelvin? So I'll do the first one and then y'all can do this second one. So for the first one, part A, we're told that it satisfies Carnot's relationship. So I'm just going to go ahead and rewrite this. Okay. We need to figure out how much heat it supplies to the room. So we need to solve for this. And we've been given all the other information, so this is going to be a pretty easy calculation. I think the worst part would just be trying to rearrange this to solve for QH. But QH is work divided by 1 minus TC over TH. Not that bad to rearrange. Let's plug in the information that we know. We know that 275 joules of work is done. And we know 1 minus, okay, the cooler temperature is 273 Kelvin. That warmer temperature is 293 Kelvin because we are looking at part A, and here's our information. So when we do this, we're going to find that QH equals 4030 joules, and that's at 273 Kelvin. Okay, so now y'all go ahead and try part B and hit play when you're ready. All right, after you solved for part B, you should have found that the QH for part B ends up being equal to 2690 joules. The only difference in part B and part A is that you just replaced your temperature, your cooler temperature with 263 Kelvin instead of 273 Kelvin. And you'll see in our results that the warmer outdoor temperature, so this 273 temperature, allows for more heat to be given off to the room. Why? Because the same amount of work is being done in each scenario. That has not changed. So when the same amount of work is being done, then you would expect this result to have happened, that the room that's already a little bit warmer, it will have an easier time heating up than the room that is a little bit, than when the outdoor temperature is a little bit cooler. Sorry, I just said that backwards, but I hope that made sense. All right. So I went ahead and revealed the sketch for this next problem. Oh, I actually meant to reveal that for this problem so you could see what was happening. So this, for the heat pump, and I'm just going to go ahead and explain this, we had the outside air that was being brought into the heat pump. Some amount of work is being done, and then that air is now warmer and it's going into our hot reservoir, which is considered the inside air because that is where the temperature is warmer. So that's what's happening in a heat pump. And I should have revealed that earlier. Sorry about that. Okay. And in this final problem, we have a hot reservoir at this temperature and it's transferring 1050 joules of heat irreversibly to a cold reservoir at the temperature 305 Kelvin. So this is a real process. We want to find the change in entropy of the universe. So to begin, let's sketch this. And I'm just going to go ahead and show you an image. So here we have our hot reservoir and we know the temperature. Here's our cold reservoir, which is at 305 Kelvin. And this is the amount of heat being transferred between the two. So we want to find the change in entropy of the universe. To find delta S, we're going to do a couple of things. So first, we're going to find the delta S for the hot reservoir. Then we're going to find the delta S for the cold reservoir. And then when we put them together, we're going to see what the change in entropy was for the universe. So the hot reservoir, we're going to have delta S is equal to negative Q divided by TH. Now, why did I put a negative sign in front of Q over TH? That's because heat is being given off by the hot reservoir. It's being given to the cold reservoir. So we are losing heat, which means that this is a negative Q. Let's plug in what we know. So here's our heat, and here is the temperature of the hot reservoir. So that's negative 1050 joules divided by 576 Kelvin. And the delta S here equals negative 1.82 joules per Kelvin. So that negative is very important, and you'll see why at the end. And this was the delta S for the hot reservoir. Now we need the delta S of the cold reservoir. So when we do this, it's going to be Q over TC. This will be positive because the cold reservoir is absorbing heat. So this Q value is going to be positive. Okay, so here we now have a positive 1050 joules, and the temperature from the cold reservoir is 305 Kelvin. So we solve for that, and we find that the delta S of our cold reservoir is 3.44 joules per Kelvin. Now let's go ahead and find the change in entropy of the universe. So to do that, we're just going to add both of these together. So our hot plus our cold reservoir temperatures, which ends up equaling, I do not know why I just wrote an 8. It would end up equaling this. Which that should look a lot more familiar to you because this is what the formula from the concept video looks like. But let's just take that information. Negative 1.82 joules per Kelvin was the change in the hot reservoir. In the cold reservoir, it was 3.44 joules per Kelvin. And when we do this math, we will find that the delta S of the universe, so the total change in entropy in the universe, is going to be 1.62 joules per Kelvin. So even though we saw an entropy decrease in the hot reservoir, we saw a large increase in the cold reservoir. So we know that we're going to have an overall entropy change of 1.62 joules per Kelvin. And this is consistent with the idea that the entropy of the universe is forever increasing in any real system, which irreversible means it's a real system. If y'all have any questions, please be sure you reach out to me. This will be the last lecture video of the semester. So thank y'all for watching and be ready for your quiz.